Okay, so let's move on with the next talk by Galin Gyulchev on images of thin accretion disk around Kerr black holes with synchronized scalar hair. Please, you have the floor.
So, first of all, I want to thank you for the invitation and to give me a talk to this nice conference. So today I want to speak about the problems for the creation of the images directly and to the indirect relativistic images of the compact objects which are similar to the objects of Kerr black holes with scalar hair. So why this is so important? Because if we take, for example, the general theory of relativity, we know in general what is the shape of the shadow and what is the shape of the accretion disk and what kind of characteristic they possesses. But if we add to the general theory of relativity some additional scalar fields, we can understand and to model how they depend not only on the characteristic of the scalar fields, but we can introduce some new quantity which is called target spacetime, which is characterized and can be created because of the existence of this scalar field and to introduce so-called Gaussian curvature and to see what will happen after that. So this work is based on a joint work with Donnelly from Tübingen University and her PhD student Lucas Kovalev and Professor Stoichi Yazadiev and Professor which is here. So every one of us know why the shadows and the images in general are so important. So first of all, we know that we can extract information about the mass and the spin parameters because of the images. But in addition, we know that we can extract the information for the multiple moments of the objects. And in addition, we can understand what is happening with the shadow, not only when we have only a black hole solution, but when we considering an object which doesn't possess horizon as the naked singularities, and moreover to consider what is happening with the shadow and the accretion disk of the different kind of wormholes. So the most important thing is if we forget for all these situations and we take one simple black hole from the general theory of relativity and we want to model the behavior of the matter around the object, we can consider the existence of scalar fields which can be considered as an external gravitational field which can interact with gravitation of the black hole and to model the characteristic of the shadow and of the accretion disk. So we know in a very good way of the papers of Cunha and there that these interactions can give the appearance of the multiple shadow images, which we can see here in our study. So the purpose of this talk is in general to give explanation how we can obtain images this one, which in general represents in the central part the appearance of the shadow in inclination of 80 degrees. So the observer is inclined with respect to the equatorial plane and 80 degrees. And in general, we see that the accretion disk has this form and it looks as the accretion disk of the Kerr black hole, but in the central part it resembles the exact shape of the shadow, which comes because of the existence of these additional scalar fields. So the purpose of our examination is to introduce somehow this scalar field. So in general, our idea is to consider dynamical scalar fields, which can be n numbers. Because of this, we can consider n-dimensional abstract Riemannian spacetime, which possesses target space with some specific Gaussian curvature, which we are going to consider after it. This is the action of theory, and because of these scalar fields, we can use some potential. So we are going to consider some standard form of the potential. So these are the equations of Einstein, and these are the equations which govern the behavior of the scalar field. Inspired by the works of Heideiro, we will restrict our consideration only to the study of two number of scalar fields, which means that the situation looks effectively to consider only one a complex scalar field, and these two scalar fields to play a role of as real and imaginary part of this complex scalar field. From other point of view, we can choose some special coordinates which can give to us opportunity to consider the metric of this target space-time in this form, where omega is the conformal factor, which can be represented in this form, where we can see that it depends on the amount of the scalar field and depends on the Gaussian curvature of the target space. Which means that if really we use this model, we can change the hairiness of the scalar hair, and for some given mass of the scalar hair, we can introduce in addition the Gaussian curvature of the target space, and to see what will happen with the models after that. If we use this standard form of the massive scalar fields, after that we consider this general form of the axially symmetric metric, where only the coefficient n has this analytical form, h is in these coordinates, and the other coefficient f1, functions f1, f0, and f2, omega, are numerically known, and they depend on the coordinates guaranteed. So which means that in order to understand what is happening with the images after that, and to be possible to reconstruct the images, we have to interpret this metric in order to work analytically with it. The scalar fields, how I said, are time dependent, so we can use distance zats in order to model the two scalar fields. C is the magnitude, and omega s, the most important quantity here, is the frequency of the oscillation of the fields, and the integer m in our situation will be taken to be equal to 1 for simplicity. Another interesting thing is that the scalar fields are synchronized with the circular velocity of the horizon, which means that the frequency of the oscillation is equal exactly to the circular rotation of the in order to reduce the number of the parameters in this study, we have to consider some smart interaction between all the parameters inside, because we have a lot of huge number of parameters. So because of this, we introduce this normalized charge, which gives to us opportunity to understand how hairiness is the solution. So in general, it can be defined with this ratio here, where J psi is the angular momentum of the scalar fields, and G is the total angular momentum of the solution. Or besides, we can introduce it in the other way, considering the conserved not a charge. Here in this plot, we can see in general two different situations. So for example, the red curve represents the solitonic solutions, which represents the boson star solutions, and the other situation which we are interested for are shown with yellow color, which gives to us the opportunity to consider different black hole solutions possessing different horizon, but in addition to this, and solutions which have different normalized charge. Because of this, we choose with the red dots some solutions which are interesting somehow because of the charge which they possess, and we're going to make the reconstruction. So here after, all the things which we are going to speak about are known for every one of us, so they are standard. This is the standard methodology which first we consider the metric in this general form. After that, we are going to introduce the effective potential of the massive particles, because we wish to make the reconstruction of the thin accretion disk around these compact objects. And inspired by this idea, we apply these simultaneously conditions over the potential, and finally we can understand where exactly exists the circular orbits into the accretion disk and when they are stable or unstable. So if every one of the particles is assumed to move in a circular orbit with Keplerian velocity omega, we can calculate from the system applied for the potential these integrals of motion, and knowing the Keplerian velocity of the oscillation to understand really where is the position of the circular orbit over the accretion. After that, the task is split to the second part, so the part which is related with the emission of the light rays. So if we know where exactly are the position of the massive orbits, we can assume that we have emission of this structure of orbits, which we call thin accretion disk, and after that to understand what is the behavior of the light rays in this space-time. So following the work of Kunia, which is really very inspired work, because it introduced a very good opportunity to work with, for example, two special parameters, which is very easy explanation of this, how we can reconstruct the shadow. So first of all, we consider the Hamiltonian equation. After that, because the Hamiltonian for the light rays is equal to 0, we can introduce this effective potential. After that, to introduce the auxiliary effective potentials, and applying the conditions for the circular orbits of the light rays, we can predict where these circular orbits exist, and finally to understand are they stable or unstable in terms of this auxiliary potential. So making this, for example, in some for some Gaussian curvature, for example here k equal to -5, we make this potential, and very clearly we can see because of the local maximums of this potential, when we have opportunity to observe light rings, and because this potential depends on the whole variety values of theta and r, where r is unit dimensionless coordinates, we can see really where exactly there exist stable or unstable light rings. And for example, considering the picture on the right-hand side, we can see the eternal light ring, which is a saddle point, so it is stable in the radial direction, but unstable in the theta direction. After that, we can see the second inner light ring, which is again a saddle point. From the same sense, we can see and to calculate the outer light ring. And the most interesting thing here is that there exists one stable light ring, which is the second one from outside from outwards to inwards. So, with other words, we have a composition of 4 number of light rings. The outer side is unstable. The second The second is stable white ring, and after that we have two inner unstable white rings. So this gives us opportunity to consider very interesting behavior of the white rays. Because if we make simple ray tracing of a point which emits white rays of the accretion disk, we can visualize directly what is happening with the distribution of the photons and really which white ring acts as unstable and which acts as a stable white ring. And after that, to give very intuitive and, simply speaking, a clear understanding how the shadow is created or the image of the accretion disk. So again, considering the type of Cunha, we can introduce all the needed quantities which relate the components of the photons momentums, and to introduce this parameterization of two impact angles alpha and beta, which gives us opportunity to make a simple ray tracing. Every one of the momentums introduced via these two angles, alpha and beta, in general gives us opportunity to relate these two angles, alpha and beta, with the observable quantities. And if we parameterize the integrals of photons motion with these two angles, alpha and beta, finally we can solve the first task and to relate the observable quantities x and y, and to make the mapping via these two impact angles alpha and beta, and to see what the distant observer will see as an image. And in general, this is one of the results. So here, from the right-hand side, we can see how we look the shadow. Exactly, for some Gaussian curvature, in this case, the Gaussian curvature is equal to 0. So we see that the shadow has this famous hammer-shaped shadow, but here is a little bit difficult because I chose some different values of the normalized charge. And in the left-hand side, we can see some interesting reconstruction, what really is happening. So first of all, I consider here some arbitrary orbit which should exist into the accretion disk. It is shown with purple color. And inside, we can see some orange orbits which represent the position of the white rings. So if we want to represent these white rings and to understand how they really look, they look exactly in this way. So they are defined, first they exist only into the equatorial plane. So we can see from the auxiliary potentials that they don't exist outside the equatorial plane. So they are two-dimensional structures, simply speaking, and can be represented in this way, where this outer orange circle represents the outer unstable white ring. And the other interesting thing is here, very close to the horizon, we can see second inner stable white ring. And if we choose some emitting point from this trajectory of the particles inside the accretion disk, we can see in the point of this position how the shadow should be created, or what can see this point. And these two lines, for example, give us opportunity to understand which trajectory goes exactly and will hit horizon and will be absorbed of the black hole, and which are scattered whole, and they are shown with colors. The most interesting thing here is that we have to give simple explanation why the shadow possesses multiple components. So, for example, from here, if we take one vertical line for some specific impact parameters, for example, impact parameter beta, and arbitrary values of the parameter alpha, we can make one two-dimensional surface of white rays, which is made of white rays, and for some specific impact parameter to see what will happen. So we see exactly this picture. But we see that we have, for example, three different channels. We have one channel above, we have one channel below, and one wide channel in the middle part, which can give explanation why here we have a shadow above, shadow and shadow into the central part of the object. And in order to give more good intuitive explanation, this animation at which we can see what is the interaction of the white rays from this surface with the white rings into the equatorial plane. And if here in this picture we decrease the impact parameter beta for these two angles, in general this surface of white rays is going to be more and more closer to the black hole horizon, which means that some of these white rays hit every one of the white rings, and we have this very complicated behavior of the whites. So maybe one of the most non-standard situation here is the existence of the stable white ring, which here reveals how much of the orbits can interact with these stable white rings, and why the image is so complicated, and why the image reveals this chaotic geodesic, which appears simply speaking randomly over the image, over the shadow. So they are very sensitive about with respect to the changing of the initial conditions, and looks as a chaotic behavior over the shadow, which is because of the existence of this stable white ring and this complicated behavior of the orbits. Okay, after that, in order to understand what is happening with the accretion disk, we follow the simple model of Novikov-Thorne for a thin accretion disk. So in this formula, we can see the radial distribution of the energy flux created from this thin accretion disk. And if we know the Keplerian velocity of rotation of the particles inside the disk and the integrals of motion, the energy and the angular momentum of the particle, we can calculate the emission. And here I can give a short explanation. Is this easy or no? So if we just take the formula and substitute all inside the formula and calculate the flux, so it's easy, yes, but here in this task, which involved scalar fields, the problem is not so easy, because the Keplerian velocity of oscillation of the particle can possess disconnections for some position of the orbits, which means that the disk possesses a discrete structure, and there is places where the stable orbit doesn't exist, which means that we have to decide which part of the disk which we have to study, and for example, to examine the behavior of the Keplerian velocity, which can give appearance of local maximums, which can contradict with the solutions of the equation for the innermost stable circular orbits, and we have to be very precise from mathematical point of view how we can extract physical information about these solutions. So because of this, here I choose some values of the normalized charge which give more simple situations, and after it we can see the final result. So first, if we take this solution for this behavior of the radial distribution, after that we can take into account the gravitational redshift, which is given with the standard formula, give opportunity to understand with the particles which are moving in counterclockwise direction and direction synchronized with the rotation of the disk. The observer can see a different flux because of the gravitational redshift. And finally, if we introduce the different profiles of the radial distribution, we can see that the profiles are not the same for the different charges. So, for some charges, the maximum value of this radio distribution really can be very huge. It can be very huge than the Kerr emission, but for some other charges, this emission is suppressed. So the second important thing is that the profiles, some of the profiles are very wide, but some of the profiles for some charges are very narrow, which really can play important role after that over the observations. And if we compare these flow fluxes, they look in this way. So for some charges, we have bigger emission. For some of them, emission is very strongly suppressed, and it reveals the behavior of the Kerr emission. And the images finally looks in this way. So if we start from a very huge normalized charge, which is very close to the boson star solutions, so we can expect a really very small shadow. So the shadow almost should disappear in these cases. Because of this, here we can see very small dark area, and if we make the disk to be artificially transparent, we can see all the other relativistic images which resemble how the shadow will look in this inclination of 80 degrees. So we really see the shadow which resemble this chaotic behavior of the geodesics, and it is very, very small, but possesses a lot of different number of components. After that, if we decrease a little bit the normalized charge, the shadow is going to decrease a little bit, and if the disk is transparent, we can see this image of the shadow. And the flux, we have to remember that the flux is not distributed into the same way. So for some higher charges, the distribution of the flux is very narrow. But if we decrease the scalar charge, the flux is a little bit more widely distributed. After that, if we decrease more the normalized charge, the disk possesses this structure. So we can see that here the flux is more widely distributed, and the shadow, the dark areas into the shadow becomes a little bit more wider. And again, decreasing the scalar charge, the shadow is going to increase a little bit, and the distribution is going to resemble probably the distribution of the Kerr solutions. And if we decrease more the scalar charge, now we can see first we can see that we have only two unstable white rings, which is really the situation for the Kerr solution. And we see this O-shape form of the shadow, which really intuitively can give to us the idea that we are going to follow the behavior of the Kerr solution. And finally, for relatively low value of the normalized charge, we see this disk where the emission is more widely distributed here. The maximum value is not so higher, so it resembles the Kerr emission of the disk, and the shadow is really more oval. And finally, I can resume shortly what we obtained. So in general, the results for the accretion disk follow exactly the results for the shadows. Where in addition, here we have a different distribution of the flux. So for some values of the charges which are relatively higher, the emission is relatively stronger, so it's higher than the Kerr emission. But when we decrease enoughly this normalized charge, firstly, the chaotic behavior of the geodesic is going to disappear because we didn't have stable white ring. So it appears because of the appearance or the existence of this stable white ring. But if this stable white ring disappears for some relatively smaller values of the normalized charge, we can resemble the behavior of the emission into the Kerr matrix. Also, this all these results, all this variety of results really can show to us that if we tune the value of the normalized charge and, for example, moreover, the Gaussian curvature, really we can model into in a good way results and probably to fit the